Good morning, ladies and gentlemen, and thank you, Andreas, for your kind introduction. And as we've just heard, about a year ago, the 7th billionth person was born into our world, where we use the equivalent of 1.5 planets worth of resources each year just to provide what we need. This means it takes the Earth 1 year and 6 months to regenerate what we use in that given year. And if we continue on this same path, when we meet at 35 years from now at the 45th Energy Conference, we'll be using 2.5 planets worth of resources to support 10 billion of us. We will have tripled our energy use, turning life-sustaining resources into waste faster than can be replenished puts us in danger of global ecological overshoot, depleting the very resources upon which all of us here depend for our survival. You see, global population growth and economic development is unrelenting and unforgiving. And sometimes just thinking about the numbers involved, billions, is simply too large for us to understand. There's 7 billion people. And we all know that if you're the last person at the back of a line of 7 billion people at Starbucks, they'll be out of coffee by the time you get there. Hard to visualize how many resources 7 billion people use. Perhaps if we look at this in a different way, 7 billion of us, if we stand shoulder to shoulder in a line in front of us, a line behind us, a line below us, a line on top of us. We, 7 billion people in these lines, will fit, with a bit of a squeeze, into a cube, 1 mile wide, 1 mile deep, 1 mile tall. A cubic mile of people. This cubic mile of people, us, you, me, we use 3.5 cubic miles of energy a year to sustain us. We get 1 from oil, 1 from coal, 3/4 of a cubic mile from natural gas, 1/4 from hydro, 1/4 from nuclear, 1/4 from burning. Less than a tenth. Less than a tenth. In 35 years, we will double this. Now, we can do more of the same and most likely destroy our world in the intervening time. Or we can install alternatives. Alternatives to get that extra 3.5 cubic miles. So what would it take for 1 cubic mile? We'd have to bring on hydro, 1 every quarter for 50 years, a nuclear plant, 1 a week for 50 years, 3 solar plants a week, every week for 50 years, 1,200 windmills a week for 50 years, and 250,000 homes per day for 50 years. I don't know about you, but when I look at this, it doesn't seem like we're going to get there. Not surprisingly, we've seen a dilemma like this before. In the early 19th century, cities around the world depended on thousands and thousands of horses to transport us around. In London, for example, there were 11,000 horse-powered cabs. There are also 7,000 buses, each of which required 12 horses per day, for a total of 50,000 horses. Now, the problem, of course, was all these horses produced huge amounts of manure. A horse, on average, will produce 25 pounds of the stuff a day. Consequently, the streets of London were covered with it. Writing in the Times of London in 1894, one writer estimated that in 50 years, every street in London would be buried under 9 feet of manure. Civilization was doomed. Of course, we know it wasn't. The great manure crisis vanished when millions of horses were replaced by automobiles. Our similar crisis is this. And the pressing problem we all face is trying to find our equivalent of the first car. Just the first car. Now, I believe the answer can be found in the building blocks of the universe, which began 13.7 billion years ago. I think the answer is there. It's difficult to grasp a timescale of 13 billion years. Carl Sagan made it easier when he said, just think of 13 billion years as if it happened in one calendar year. If we look at it this way, it's a millionth of a second after midnight. January the 1st, there's nothing around us, not even time or space. I want you to imagine the darkest, emptiest thing you can, and that's where we are today. It's unbelievably hot, 10 to the 32 degrees Celsius. It's under immense pressure because all the building blocks of the universe that become you, me, your cat, your dog, your house, your office, everything is squished into a space smaller than a single atom. It explodes. In less time than it takes to blink your eye, space grows from the size of a pinhead to the size of a galaxy. 3 minutes later, the temperature has cooled to a balmy 1 billion degrees Celsius. A magical number, actually, because it allows two critical building blocks, hydrogen and helium, to form in huge clouds with no structure, but that have areas here in blue that are a fraction of a degree cooler than the red areas, which is just enough for gravity to grab hold of, compacting these clouds. As each cloud compacts, gravity gets more powerful as density increases, and temperature begins to rise again until there's another huge release of energy. And on January the 13th, we get light, stars, billions of them light up the universe. Because temperatures are so high, these building blocks that are scattered everywhere start to fuse together in exotic combinations. And if any of you are wearing gold, just remember it was forged in these supernova explosions. Now, this galactic mixing process continues for the rest of January, all of February, March, April, and May, until we get the first galaxies appearing. We've taken 4 months, 4.5 billion years of building blocks just to get here. It takes another 4.5 months till September the 14th for our solar system to evolve. And on December the 1st, we get the huge building block, oxygen. It's taken 11 out of the 12 months to get to this one critical step. 16 days later, we get the first single-cell organisms. On Christmas Eve, rowdy teenagers appear and start trashing the neighborhood. Four days later, an asteroid slams into the Earth. The result, a dinosaur barbecue. The sun rises on December the 31st, last day of the year, 10:30, still no signs of humans, until somewhere in Africa that night, the first hominid leaves the dinner table and stands up. We call her Lucy. With 10 seconds to go before the year draws to the close, America signs the Declaration of Independence, finally providing them some history to talk about. With 3 nanoseconds to go, Roger Federer wins his 7th title, and then on the stroke of midnight, we arrive at the crown jewel of 13.7 billion years of evolution. Now, I know you spotted that I've left out a couple of things along the way. And one of those things that I left out along the way was this guy, who in 1905 was just living down the road at Cramgrassa, where he developed his special theory of relativity that described the relationship between space and time. And it was this theory that ultimately led Richard Feynman to wonder about the building blocks of the universe. December the 28th in 1959, he gave an after-dinner talk and described from what was known about science at the time. Now remember, this is when a calculator was the size of a typewriter and a computer was the size of a very large room. And when he describes this, he theorizes how you could write all 24 volumes of an encyclopedia on the head of a pin. He ended the talk by saying one day we would have the ability to rearrange the very same building blocks of the universe, the ones that took 13.7 billion years to come into being, and be able to make things with incredible strength and properties never before thought possible. He thought cutting down large trees, what a waste that would be to put it through a sawmill to be able to make planks of wood. Why not just start from the bottom up? Put atoms together one by one and create the table. Anybody listening to him at the time must have thought, if they were being polite, gosh, he's absurdly imaginative. The not so polite ones would have been silently laughing at him, thinking him utterly crazy. 15 years ago, I was on a train reading his speech, and I thought, what if he's right? And that question led me to form Nanoholdings. Because what really Feynman was talking about was, what's the difference between a world where the difference between what is worthless and what is valuable is merely the addition or subtraction of a few atoms? What dawned on me was what Feynman already knew. Nature does this all the time. By rearranging the structural position of, say, carbon atoms in a lump of coal, you get a diamond. In our labs, we've rearranged these same atoms and made a unique form of carbon in this amazingly beautiful process where we take a powerful laser and unleash 3.3 gigawatts of power in just 9 nanoseconds. The carbon we make is a tube-like structure. It's made of carbon. It's, instead of black, transparent. It's 100,000 times smaller than the width of a single hair. It's 100 times stronger than steel. It's 1,000 times more conductive than copper. Making these magical properties is something that took 13.7 billion years in the universe, is exactly what Feynman was talking about. But now we have these incredibly electrically conducting materials with these fabulous properties. What do you imagine you could do with them? Well, for starters, we could start trying to solve some of these problems. We spend an awful lot of money heating and cooling our buildings, and as the world's climate reaches greater extremes, these bills, and I'm not just talking about the money ones, will continue to increase. And it would be really helpful if we could reflect away the heat, infrared, from outside a building in summer at the flick of a switch. Like with this. A rollable, flexible film. It's in the early stages of development that could stick to a window, stops any light and heat coming through when it's tinted, or all light and heat through when it's clear. In fact, you'll be able to dial the dial to any setting of light and heat or cooling you wish. We'll have to be also able to think differently about light. This is a huge waste of energy. But to turn off all these lights, it means we're going to have to change what it means to see. Now, not long ago, if we tried to download Star Wars via a modem like this, and yes, there are some of us that actually did use this, if we got it over that modem, it would have taken us 9 days to get the movie before we could watch it. Over broadband, we start playing in 36 minutes. So when I said that word broadband, you instantly know what I'm going to. Because you see, in our universe, broadband is everywhere. Energy is zipping all over the place. Now, some energy bands are really, really small and they move really, really fast. Gamma rays. If you stand in front of a gamma ray, you cook. A little bit further out on the spectrum, sunlight, if you stay on the beach a little bit too long, you also cook slightly less fast. In between, there's an energy band between 400 and 700 nanometers, which makes up a tiny, tiny, tiny fraction of what hits us, but we see it. But it's still energy that our eyes interpret as color because of specialized cells on the back of your eye called a photodetector. Now, these cells act like test tubes of different colored liquids. When wavelength for blue pops into our eye and hits these tubes, it makes the blue tube and only the blue tube vibrate, which gets picked up by a synapse that fires off an electrical signal, and someplace in our brain it says, "Oh, I saw blue." Well, one of our scientists thought he could replicate that idea on a thin film covered not in test tubes of colored liquids, but instead with quantum dots, atomic scale dots, that can be tuned to pick up energy, just like tuning the dial on a radio. Now, the implications of this is pretty huge. It means that if you can shift wavelength of how you see, windows that you see through by day can become light emitters by night. It means that solar cells that only used to work in sunlight could instead grab energy from other parts of the spectrum at other times. All in all, it means broadband sight is a paradigm shift that expands what it means to see. Perhaps this type of thinking should also shift how we think about our environment in a different way. Now, for many years, we've been told about the harm of CO2 emissions and what they're causing. So much so that the data has become overwhelming. I mean, how on earth are we meant to grapple with something like this and think that our individual contribution counts at all? At University of Arizona, Arizona State, they've created software that might change that. It's called Hestia. And it starts with the premise that you can't reduce what you can't easily measure or easily visualize. Sorry. This is Indianapolis. Normal city. Cars, trains, factories. This is Indianapolis through Hestia. Buildings that are emitting. Which buildings are emitting CO2? Which houses? Which industrial buildings? Airports. How they're making their CO2. How does it relate to each other? When does it relate to each other? During which part of the year? Now, once city planners and regulators can see the problem, it is hoped that they may make more informed decisions about their carbon mitigation efforts and perhaps provide large and valuable tax and regulatory incentives for novel building solutions, many times than are available today. Now, we need them now. We need them now, those incentives. Let me give you a case in point. A few years ago, we funded a remarkable scientist who had spent a considerable amount of time thinking about the ways to reduce CO2 that results from making cement. That's a hugely intensive process that essentially involves digging up a mountain of rocks, crushing them up under intense heat, making a powder, transporting that powder out to a job site, adding some water, fizz, and essentially taking the mountain, creating another mountain in the form of a building. Unfortunately, for every ton of cement that goes through this manufacturing process, for every ton, we release a ton of CO2 into the atmosphere, and it accounts for 5% of worldwide CO2 emissions. Now, our scientists' idea was to take the byproduct of another polluting industry, burning coal to make electricity, and instead of dumping the toxic fly ash that comes out into a landfill, which only ends up in these pollutants ending up in our water supply, what if you could take, at its atomic level, fly ash, which are silicates, ball-bearing-like things, and sort of rough the edges up. They call this functionalization because scientists need big words, but it's rough it up and make it stick together like Velcro. What if you could do that? And what you make is environmentally friendly cement that releases almost no CO2. It's equally as strong, it sets many times faster without releasing any heat. For anybody in the building industry, you've saved a lot of throughput time. There's a catch. The catch is the cost of this is 40% greater than the cost of normal concrete. And as far as I now know, it seems that 40% means most people don't care. Just not enough incentive for people to switch. Now, nature has a way of making us pay attention even when we don't want to. 40% of the world's population lives within 60 miles of the sea. 10% are going to be directly affected by rising sea level, and more frequent and powerful storms are going to inflict immense misery on another 30%. Sea barriers, that's one way to solve the problem at $19,000 per square meter. Nature's answers, reefs, which we, as a society, are continually destroying, are able to dissipate 97% of the energy of storm surges. And they do a fabulous job, which got us thinking, with our company that couldn't go anywhere because it was just a tad too expensive. What if we took the same manufacturing process that we're doing on fly ash and take it and try it on a bucket of sand from the beach? Would it make natural, strong, dune-like barriers either onshore or off? And it turns out it does. So we've now completely shifted the direction of this company, and we're developing solutions that hopefully in the next 5 to 10 years will create natural sand reefs wherever you want them. As delighted as we were about this chance discovery, we know, given the scope of the challenges we're facing, that finding solutions via trial and error like this, mixing and matching stuff, is long and arduous. And I alluded to that a little bit when we were talking about the window coating. You see, it's just difficult work. And part of the difficulty is, while we know what all the building blocks of the world that we have to use, and we know mostly what just two, when they're mixed together, make, if we try and get more esoteric compounds, adding 3, 4, 5 elements, we know almost next to nothing about their properties. Which means we've got a quadrillion possible things to go try to find the next skin. And then we're not going to find them quickly enough if we have to go through a quadrillion by trial and error. So for a number of years, we've been building something called Magenta to mathematically target and expedite this discovery process to shrink the time for discovery. Now, let me give you an example. Let's say we have some features we want, say a novel building skin that must be blue, electrically conducting, and let's say it's got to be hard as titanium. Now, magenta translates this into a series of mathematical equations and points you to the only possible places in the periodic table where you could mix that lot together, blue, electrically conducting, and titanium. It then builds you a recipe book of what to go mix, and it'll even calculate the crystalline structure of the material, all of which has happened on a computer before you've done anything in the labs, helping you and your company to be able to get greater insight at the tip of your fingertips. With each new discovery, it may well change everything that we once held as fact, like what happened in 1929. After months looking up the night sky, Edwin Hubble realized that the galaxies were all moving away from him. Up until that point, you see, we'd all been taught at school that space was static. We were a fixed place and that was it. Of course, when Hubble discovered that that wasn't the case, every textbook had to be thrown away. And for the next 60 years or so, we were all then taught that while space was expanding and pushing us further away, the rate at which space was moving was sort of slowing down. And at some point, we would all collapse back in together, being squeezed together with our closest friends. Well, a few years back, two other scientists set out to measure how fast it was slowing down. I suppose they wanted to find out the date, life was over. Well, guess what? It's not happening. Space is actually expanding faster and faster. That's like tossing an apple upwards, and it just keeps on going. Now, the implication of this discovery is staggering for all of us. The only way an apple that keeps on moving away when I throw it up, accelerating as it goes, is to have something huge driving it. Which means that the dominant force in this universe isn't gravity. It's something else, and it's not trivial. Far from it. It makes up 73% of the whole universe. It repels gravity, and it's invisible, which is why they now call it dark energy. And if that isn't bizarre enough, dark energy's cousin, dark matter, yes, you guessed it, you can't see that either, it makes up 23% of the universe. Talk about a cruel joke. For centuries, science has been creating theories to explain what we see, but has ignored 96% of everything around us that is absolutely invisible. Which means you, me, the Earth, the solar system, the galaxies, everything, we make up a piffling 4% of what's actually in our unique neighborhood, where the sun provides every moment of every single day 10,000 times the world's energy needs. Now, to give you some idea of just how much energy that is, imagine a road from here today connecting us to the sun. Now, this road is made entirely of ice because we're all driving down this road. It's 2 miles wide. It's 1 mile deep. Now, if we left here today and started driving, in 168 years, no stop for coffee, no pee break, no sleeping, 168 years, we will all arrive at the sun. The energy from the sun will vaporize that road, 168 years long, 2 miles wide, 1 mile deep. The sun will vaporize that deep block of ice in 1 second. Our attempts at radically changing where we get and how we get our energy are still in baby steps. Now, as I closed this morning, I want to direct a question to the people in your organization, how you think of them, that create your designs, those that figure out new materials, those that are responsible for your company's success. How many of those in your organization have the type of thinking like Feynman, like Einstein, how many of them are able to see innovation leaps as grand enough, like I just described, to result in radical change? Maybe we could see as a show of hands. How many in your organization, for more than 50% of your organization, are Einstein-like? Less than 50%, huh? Well, actually, when we were in kindergarten, we all had that kind of imagination. Remember when your cardboard boxes were spaceships and your dog was your trusted co-pilot? Somewhere along the way, we have all lost our capacity to imagine. This is causing huge concerns with educators who are worried that our obsession with exam results has meant that so many of our other incredibly vital skills that we desperately need now have been jettisoned. And you're seeing exactly the same thing happen in corporate world. The exam results there, of course, being increased quarterly profits by reducing R&D funding of breakthrough imagination. If this continues, at some point, corporate R&D cupboards may well indeed be bare, which means it's vital to provide people with an environment in which they can thrive in your company to be able to dream up those valuable ideas, such that when we meet 35 years from now at the 45th conference, we will have changed everything. I would urge the great minds in this room to embrace a commitment to be part of that change. He did not say, "I have a plan." He did not say, "Let's go halfway." No, he didn't. Thank you.